Okay, so yesterday we started talking about differentiability, and so what I'm doing here is I'm taking the definition of differentiability for single variable functions, interpreting it diagrammatically, and then extending that diagrammatic idea of differentiability, that sort of visual idea, to two variable functions. So here what we had was a curve and a tangent line. For two variable functions, that would step up a dimension to a surface and a tangent plane. So if we extend this visual, or diagrammatic, or graphical, however you want to describe it, this visual, not definition exactly, but this visual description of differentiability, to two variable functions, we can arrive at, we can derive is far too technical a word. We're not deriving anything here. We can arrive at the following expression. Okay, so it was, the previous expression was a function value minus its linear approximation over that little horizontal distance, which was h. But in this case, it's going to be the limit. It's not just h, it's h and k tend to 0, 0 of f of a plus h. Oh, sorry, there should be a comma, not a closed bracket. B plus k minus f of ab plus h f x ab plus k f y ab over square root of h squared plus k squared. So let me explain what's going on in there. What we have over there is we have an actual function value as the first term in the numerator, minus what we would be getting if instead of reading off the actual function value, we read off its linear approximation, where this little h, if we actually did a sort of formal derivation, this h would have been something like x minus a, and this k would have been something like y minus b. Think about how in the single variable analogy above, if I have an x value, if I have an x, let's call it x naught. If my x naught is a plus h, then h is x naught minus a. So that's the kind of thing that's happening here. I'm just going to scroll up to the single variable expression that I wrote down yesterday. No, I did have an h in there. I was thinking I had an x minus h, but in fact I do have an h. So see that single variable expression at the top there? Okay, see how in that that bracket in the numerator, I have a function value plus h times a derivative. What I have here is the same thing, only with one more term added. I have a function value, function evaluated at a point in the domain, where a point in the domain is not just x equals a, but it's x equals a, y equals b, plus h times the one derivative plus k times the other derivative. That is the linearization. That is what we would get if instead of reading our function value off, instead of reading, again, if I can just use that single variable analogy, instead of reading our function value off the actual curve, which would be like right there at the top of my screen, if instead of reading the function value of the actual curve, the actual true function value, we read off its linear approximation, in other words, where the dotted line intersects with that tangent line. Okay? But instead of having a curve, we have a surface, and instead of having a tangent line, we have a tangent plane. Once again, this links to Taylor series. And in yesterday's tutorial, I explained to a few people where this comes from. I said, notice that f of a plus hf dash is the linear approximation to f of a plus h. And if that's not clear to you, let me I'm going to just redraw this drawing. I have a curve, I have a tangent line. Here's a, over here somewhere is a plus h. Let me draw in a horizontal line as well. That distance there is f of a. I hope you can agree with that. Okay, that distance there is the y value that we would get if we plugged a into our function. Okay, this distance here is h times f dash of a. Because remember, this is similar to what I was discussing just the other day. If you have a vertical over horizontal, your slope is vertical over horizontal. So you can express your vertical distance as your horizontal distance times by the magnitude of your slope. Delta y over delta x gives you slope, therefore delta y is delta x times slope. That's what that is, h times f dash. It's slope times horizontal distance. So in other words, if you were going to read off that vertical distance there, it's f of a plus h f dash of a. It's the y value that you'd get if instead of reading off your true function value, you read off the linearized approximation. Okay, yes?
So it only goes up until the tangent line?
Yeah, because this is linearization. So let's look at it this way. We start off with our definition of differentiability. Where is it? Down here at the bottom. Here we go. We start off with our definition of differentiability. We smoosh the terms around a little bit in order to get this thing that's at the bottom of the screen. And then we say, haha, we recognize what that is. That is true function value minus linear approximation of function value over horizontal distance. Then what we do is we take that description, if you will, of differentiability, and we step it up a dimension for two variable functions. Only now instead of our function value being a point on a curve, it's a point on a surface, and instead of being our linearized approximation, instead of it being a point on a tangent line or a value read off a tangent line, it's a value read off a tangent plane. And then that little h squared plus k squared, well, if you think about it, if you drew a little, so your domain is R2, and if you have some point here, AB, and you have some other point over here, which is A plus H, B plus K, then that distance there, let me lengthen my axes here. Just want to lengthen them a little. So there's A plus H, here's B, here's B plus K. That little distance there is h, that little distance there is k. Pythagoras theorem says that little distance there is h squared plus k squared. That's where that square root of h squared plus k squared is. It's the distance between our points of tangency AB and our point that's some little distance away. And what we're doing is we're looking to see, again, this is all about differentiability. Think back to when you probably your very first lesson you ever had in calculus. It would have had a picture like this, something like this. It would have had a secant, and you would have said, okay, this distance here is h. What happens to the slope of the secant as h gets smaller and smaller, and you'll end up with the slope of a tangent. If you think back to almost certainly the very first lesson you ever had on calculus back in matric or whenever it was you did calculus for the first time. So what we do is we take that little distance in the domain and we make it tend to 0. But here our little distance in the domain is not just h, it's not just k, it's the square root of h squared plus k squared. Okay, all right, so I spent a lot of time justifying that formula, but fundamentally that is a very important formula. And we say a function is differentiable at AB if the limit, this limit that I've just written and I'm about to write again, f of a plus h, b plus k, minus f of ab, minus h times the x derivative, minus k times the y derivative all over that little that little distance in the domain equals 0. Yeah, if and only if. If and only if. 2 f's in the word if means if and only if. Okay, now this formula has a little bit of a history. This course hasn't really changed. For years and years and years, this course has remained the same. And in fact, frequently it's the same people lecturing it year after year, going back in the maths department. And so sort of traditions develop. And so there's a tradition to call this formula the beast. So when I started teaching this course, I said, no, that's a terrible name. I mean, how can you call it the beast? Well, first of all, it's not particularly beastly. Secondly, if you go in calling it the beast, you're going to go in with a sense of fear and dislike, like you're being attacked. And, you know, I mean, honestly, it's not that bad a formula. And it's actually very easy to use. Often a bunch of the terms are 0. And so it's not actually particularly beastly at all. So let's give it a rather nicer name. So I asked my class to suggest names for something that is quite big and imposing, but it's not really, you know, out to get you. And somebody suggested an elephant, and I thought that was a magnificent name. So I've decided the tradition in MAM 2085 is that we call it the elephant, not the beast. Okay? And then I asked my class for what elephant is in all 11 official languages, 9 official African languages. And it was a variety of, I've written in Ndlovu there, you see. Not all the languages are in Ndlovu, but some are very similar, and so I thought, okay. And I've even seen in tests and exams, some people will say, right, now we're using Ndlovu, and off they go. But whatever you call it, you have to have this formula memorized, okay? Please keep quiet. You have to have this formula memorized. It's in the box on page 31. It might look big and chunky, like you're never going to be able to remember that, but there's a pattern to it. You know, there's a pattern to it, and you'll do it a few times and you'll realize it's not that big a deal. But you have to have it memorized, okay? So when we check differentiability, we frequently have to use this formula and check, is the limit equal to 0? Often it's not, because we deal with such weird functions. Okay, I need to say a couple of things about this. First of all, see how this formula uses the partial derivatives. So that means in order to use this formula at all, our partial derivatives have to exist. So our partial derivatives existing are a necessary condition of differentiability, not sufficient condition. It's not enough that the partial derivatives exist, but you do need it. If your partial derivatives don't exist, your function's not differentiable and you can't even get off the ground. Okay, so let's note 1. The partial derivatives have to exist for the function to be differentiable. Okay, they have to exist at that point A, B. All right? Second thing to note, which is a little bit more hidden perhaps, but let's have a look. If star, let me just put a star next to it, if star tends to 0, well that's a quotient expression, right? There's a thing at the top and a thing at the bottom. In order for something that's framed as a quotient to tend to 0, the numerator has to tend to 0. So if this thing tends to 0, it follows that the numerator tends to 0. Numerator. Which is only possible if the first term tends, or let me actually, the first term minus the second term have to tend to 0 as hk tends to 0, 0. Because h and k tending to 0 are going to deal with the third and fourth terms in the numerator tending to 0. So if our entire numerator has to tend to 0, it necessarily follows that the first term minus the second term is going to have to tend to 0. In other words, f of a plus h, b plus k tends to f of a b as hk tends to 0, 0, 0. And that has a name. That thing that I just wrote down there, that has a name. That's called continuity. I mean, I haven't written it down with fancy limbs and things, but that basic idea that as you get closer and closer and closer to AB, your function value gets closer and closer and closer to the function value at AB, that's continuity. So the second note here is that your function has to be continuous in order for differentiability to be the case. So the function has to be continuous for the function to be differentiable. So your partial derivatives existing and your function being continuous are both necessary conditions for differentiability, but not sufficient. Question? Just a number. So your partial derivatives existing means that they're equal to real numbers. Yeah.
And necessarily not the same.
Not necessarily the same. Sometimes, in fact, usually they're not the same. Okay, all right. So that's differentiability. Is there any other lead up I want to do before doing some examples? No, I've said that. I think I've said everything I want to say before jumping into some examples. So let's go. I'm going to do numbers 93, 94, 95, and they each step up in difficulty. So let's do 93 first. I'm going to do a page jump. Everybody ready for the page jump? No? Okay. I can't start without doing a page jump. I mean, I could start 93 on the very last line of the page. It seems like poor style. Okay, there's two notes there. The first note is partial derivatives have to exist. The second note is the function has to be continuous. And I'm doing a page jump. Oh, there are two lines. Okay, let me do exercise 93. Please keep quiet. The question asks, is this thing differentiable at the origin? Well, you should be able to picture that in your head and answer the question, yes. You want it bigger? Oh, I see. I suppose I could do this. Yeah. Okay, alrighty then. Now let's change the zoom. That is at 180. Let's change it to 150, and then we can do that. And that's about the best I can do, because I'm going to be writing now. Okay, alright. Moving on. We mustn't faff about. What sort of surface is that? That's a cone, okay? It's a cone with its pointy bit at the origin. Are pointy bits differentiable? No, pointy bits are never differentiable. Pointy bits is not a technical term. You will not find that in a textbook. But kinks are not differentiable in curves or in surfaces. So we can go into this knowing that this is not differentiable because we know what cones look like and we know that kinks are not differentiable, but let's prove it algebraically. If I ask you in a test, is this differentiable at the origin, I would accept a written sentence answer saying no, because it's got a kink would be a good term, but even if you just say a pointy bit. But I'm not going to ask you anything that simple, so you can relax. Okay? All right, I am going to, so the whole question is it differentiable at the origin? Hence, differentiability is in doubt, and when differentiability is in doubt, you have to work out your partial derivatives from first principles. So let's do that. dz by dx evaluated at 0, 0 is going to be the limit as h tends to 0 of that thing when, okay, so I'm going to choose to use this notation just so that I have access to this. So that's 0 plus h, 0 minus f, 0, 0 over h. The z notation is not very convenient for this. Someone's asking me a question. Yes, but I have to keep going.
The line on the partial derivative.
Hmm?
dz dx. What does that line mean?
That vertical line that I've drawn, kind of evaluated at.
Okay.
So, I'm going back to 180, by the way. I want this to be bigger on the screen. 180. Okay. Go big. Thank you. Dark blue. What'll that be? That'll be the square root of h squared minus 0 over h equals lim h tends to 0. Here's a trick question. What does the numerator simplify to? Mod h. What is the limit of mod h over h as h tends to 0? Does not exist. Why doesn't it exist? It doesn't exist because if we were going to draw that, let's draw the graph y equals mod x over x. When x is positive, then mod x is just x. So that'll be x over x and y will equal 1. When x is negative, mod x is actually negative x. It's had the minus stripped away from it. But the denominator is still negative. So mod x over x is actually minus 1. As we approach 0, our limit does not exist because a little ant walking along the function, walking from the right or walking from the left, will have completely disagree with one another about what y value they're tending towards. The limit of mod h over h does not exist as h tends to 0. The two one-sided limits exist, but the two one-sided limits disagree with one another. And then you're going to end up with that exact same thing for y, but in fact that's enough. Even if the y derivative existed, not good enough. One of our partial derivatives doesn't, hence our function is not differentiable. Let me write that down. The y derivative will be similar. You'll just end up with mod k over k. But this one not existing is enough to say the function is not differentiable. If at any point in your first year course you proved that the absolute value function y equals mod x, so in other words like a V shape, if you at any point proved that that wasn't differentiable at the point, you'll find that that little argument would have looked almost exactly like this. Because the one side thinks that the slope is 1 and the other side thinks that the slope is minus 1, and at the point they can't agree. Same with a cone. The cone is what you get if you take your mod x function and spin it round. Okay, all right, well that was fun. Let's move on to 94. 94, the partial derivatives do exist. Do I want to actually go to the trouble of working them out? I am looking at my solutions, and my solutions are all muddled. That's not the one I want. Can't find it. Doesn't matter. Anyway, would you like... So I'm going to solve for my partial derivatives and show that they do exist, but the function is not continuous. Yeah. So in fact, I could just show that it's not continuous, and then I'd have finished the problem. But I think you could possibly benefit from seeing a little bit more demonstration of first principles partial derivatives. Question at the back?
Why is it that on the previous question you used test principle and not the chain rule?
Okay, good question. The question is, why didn't I use my differentiation rules, chain rules specifically, in order to differentiate this? And that's because differentiability is in doubt. And as soon as differentiability is in doubt, you cannot trust your differentiation rules. You just can't trust them. They might give you the right answer, but they might not. You cannot trust them. But first principles never lies. First principles will always tell you the truth. But differentiation rules could lie to you if your function's not differentiable. So as soon as you don't know, you have to do first principles. You have to. Question? The question is saying, is this function differentiable? So, but if the question, but that's because, let's have a look. So, baldly, the question is asking, is it differentiable? Secondly, if you knew it was a cone, you'd know it had a point. And then if you weren't convinced that points were not differentiable, then that. But 93, you'll see, is a very lonely little function because it's the only one in this sort of suite of functions that kind of looks unobjectionable. But look at the others in this whole section of problems. They're pretty much all piecewise defined. And piecewise defined functions, there's always the danger that they're not differentiable, always. Because they're in pieces. And are those pieces joining together nice and smoothly? Quite likely not. Yeah. So the piecewise defined functions, the differentiability is always in doubt. Question at the front here?
So what happens if you don't, let's say if you don't doubt it, whether it's supposed to doubt it?
If you don't doubt differentiability, when you should be doubting differentiability, which is what the question is, and you use your differentiation rules, then you'll be unaware of the fact that the answers that you're getting are quite possibly wrong. Possibly, but possibly not. This is the whole thing. You can't trust your differentiation rules where your function is not differentiable. So if you haven't noticed that differentiability is a bit iffy, and you use your differentiation rules, then you are placing trust and touching faith in something that is possibly telling you terrible lies. So approach functions with caution when you're doing differentiation rules. Okay, but I'm faffing about, and I mustn't faff about. We're already 28 minutes past the hour. Here we go, x, y. Question asks, is it differentiable? Now, if we just page back, we've done that one. See exercise 61. We actually proved that this was not continuous back in exercise 61, and I will return to that in a moment. But let's say you're seeing that for the very first time. You look at it and you go, yeah, I think it is continuous, so I'll get stuck in and I'll work out my partial derivatives. Then what would you have? You'd have your x derivative. I am doing this knowing that it's wasted effort. H. Because I think some amongst you would like to see some more demonstration of this stuff. So I'm doing it for demonstration purposes. Okay, and then we have lim, h tends to 0. What will that be? That'll be 0 over h squared minus 0 over h, and that's just 0. Y derivative at 0, 0 is the limit as k tends to 0 of f of 0 k minus f of 0, 0 over k. That will be 0 over k squared minus 0 over k, also 0. And we say, yay, my partial derivatives exist, lovely. And then we go on to check out continuity. So partial derivatives exist. But continuity, sorry, I'm not writing properly today. Approach 0, 0 along different paths. See exercise, what did I say it was? 61. 61, and we find the limit does not exist, and hence the function is not continuous. So yes to partial derivatives, but no to continuity. The function is not differentiable. Okay. All right. Question.
How do you get 0 for the function 0, 0?
For f of 0, 0. That, I read that off here. So this, so that is that 0. Okay, moving on to 95. All right. And we've done that one as well, haven't we? Where is it? 71. F of x, y equals 95, 75. Oh, no, it's x squared y, yeah. So it's like 70 and 75. Okay, anyway, I digress. Oops. So if you've got a question like this in a test and exam and it says, is this function differentiable at the origin? You need to check if it's continuous and you need to find its partial derivatives. If it is continuous and if both partial derivatives exist, then you say, okay, there's a possibility that this function is differentiable, and then you use the elephant. And that's what we're going to do in this example. Question? Doesn't actually follow. But you can't use your differentiation rules. You just can't. So if you use your differentiation rules on this, you'd use like a combination of quotient rule and product rule, and you'd end up with a result, and that result would be wrong. Question?
Can't you just start with the elephant and then if the elephant...
Yes, you can. The question is, can you just start with the elephant and then show that it's not differentiable? Yes, you can. Yes, you can. If one of your partial derivatives doesn't exist, you'll get to the conclusion that your function is not differentiable faster. Oh, hold on. No, let me rewind. You can't just start with the elephant because you need your partial derivatives in the elephant. So you in fact have to do your partials first, but you don't have to do continuity first. You could skip the continuity bit if you wanted to. Yeah. Okay, so let's work out the partial derivatives. Do I have enough space on this page? I just want to see how much space I have. Yes, yes I do. Okay, here we go. Let's work out the x derivative at the origin. That will be, we're plugging in y equals 0, so that'll be 0 over h squared minus 0 over h equals 0. I can see my y derivative is going to be the same. Could you please keep quiet? Okay, both my partial derivatives are 0, which means they exist because 0 is a real number. Not existing happens in sort of two, maybe there's more ways, but the two common ways are like we've already seen in exercise 93, where you have a limit that simply doesn't exist because the two one-sided limits don't exist. That's one way in which limits cannot exist. The other typical way that you'll find a limit doesn't exist is, what if that was 2, instead of being 0 over k, what if it was 2 over k? And we're allowing k to tend to 0. That doesn't exist. It goes to infinity. It tends to infinity. And infinity is not a real number. So those are the two typical ways in which you come to the conclusion that the limit doesn't exist, either tending to infinity or like in 93, where you have a limit that doesn't exist. I don't really know how else to say it, where the one-sided limits don't agree. Okay, but 0 is totally fine. 0 makes us happy. Then we would check continuity. But I'm going to skip that step. See exercises 70, 71, and 75, which are all basically versions of one another, really. to see how you do that. This is basically a cubic over a quadratic. It is going to be continuous. Well, okay, let's put it this way. The limit is going to exist, and the limit is 0. And because my function is 0, it means my function is continuous. So let me rewind a little. What's the definition of continuity? The definition of continuity has 3 bits. Your limit must exist at that point. Your function must be defined at that point. And your limit must equal your function value. So for instance, in the functions in exercises 70, 71, and 75, the limit did exist, but the function itself was not defined. But here, because we've done a piecewise definition on the thing, and we've plugged the hole with that 0, where xy equals 0, we have defined our function at the point, and the function and the limit are the same. So the function is continuous. So the partial derivatives exist, the function is continuous. So now we're going to check out differentiability. Limit hk tends to 0, 0 of f of 0 plus h, 0 plus k, minus f of 0, 0, minus h of the x derivative at 0, 0, minus k times the y derivative at 0, 0, all over the square root of h squared plus k squared. Because you have to have the elephant memorized. All right? But see how almost everything's 0. Question, yes. No, it can work anywhere. So the question was, does this only work at the origin? But it's only the origin where differentiability is in doubt. Everywhere else it's fine, because our function gets a bit wobbly when it gets near the origin, or at least has the potential to get a bit wobbly, because that top piece of our function is not defined at the origin, and we're kind of trying to do a patch by putting in that second piece of the piecewise defined function. But is that patch good enough? Whereas elsewhere, away from the origin, that top piece of our function is a perfectly ordinary function with nothing funny happening. Question?
So then, when we do it somewhere else, we replace all the 0, 0s with the points.
Yes. But if we were doing it somewhere else, we wouldn't bother with the elephant, because we wouldn't be worried about differentiability. But if we want to be like really hardcore and gung-ho about this thing, yes. Instead of using 0, 0, you'd use whatever your point was. Okay. So that's going to be h squared k over h squared plus k squared minus 0 minus 0 minus 0 over the square root of h squared plus k squared equals the limit as hk. I'm just going to tidy up a little here. There's a strong family resemblance between that little denominator upstairs and the big denominator downstairs, and basically what I've got is a squared plus k squared to the power 3 over 2. Now I look at that thing and I go, okay, I want to work out the limit of that thing. How am I going to work out the limit of that thing? And we think, oh my goodness, I don't know what to do. How do I work out the limit of that thing? If I had replaced all those, if I had given you that exact function, except instead of h I'd put x and instead of k I'd put y, and I'd given it to you a few days ago, you would have known how to deal with it. You would deal with it exactly like you did exercises 60 to 69. You do the approach along paths thing. Except instead of working in xy space, we're working in hk space. Here's a domain picture. Here's h, here's k, here's the point 0, 0, and we're going to approach it along paths. Okay, however, this is actually easier than those ones we did earlier. I'll just finish my sentence. This is actually easier than the ones I did earlier, that we did earlier, because we're not just trying to see does the limit exist, we're trying to see is the limit 0. Because this big fat elephant limit has to equal 0 for the function to be differentiable. So if we can just approach along one path that gives us a non-zero limit, we're done. We don't have to see is there a disagreement. There was a question? You're fine. Cool. So I'm going to go straight for the weak point. I'm not going to approach along the h-axis. I'm not going to approach along the k-axis. Those are going to give me 0. I know they're going to give me 0. I'm experienced enough at these things now to know that I'm going to get 0. So I'm going to go straight for the weak point, and the weak point is almost always this line. H equals k is a good choice. Sometimes h equals minus k is a better choice, but you can usually get good results with h equals k, equals lim. But what do I mean by a good result? I mean showing that this limit is not 0. Because if I can show that this limit is not 0, I've shown that my function is not differentiable. So let's have a look. Oh, hold on. Let me slow down. I'm rushing, and so I'm skipping steps. Approach. 0, 0 along h equals k. K tends to 0, 0. K squared k over k squared plus k squared to the 3 over 2. Equals the limit Actually, I don't even need to write that anymore. Let me just jump right to the answer, which is not 0. That's the point. That is the point. Okay, so this lecture has been a very talky lecture for me. I just started and didn't stop. I want you to give this a go now, but that'll be tomorrow. Let me just check my notes here. Am I wanting you to give it a go? Yes, I am. So tomorrow morning what I'm going to do is I'm going to ask you to give it number 97 a try. But basically, from 96 up until 103, these problems are all in the same category. Just hold on, there's a question.
How can it be continuous but the elephant's not 0?
Well, basically, we have a function that's continuous and not differentiable. And continuous just means that there's no gap. But because it's not differentiable, it probably means that there's a kink. So there's no actual hole in the function, but there's a kink, and therefore it's not differentiable. Kinks are not differentiable. So continuity is fine, but differentiability is not fine. Okay, we might have to discuss this in our own time. I'm gonna pause. Hold on, no. I want to say one more thing. One more thing. One more thing. And in one sense, it's a sort of a style error that people make, but it's actually a logical error. Notice what I did. When I started this whole elephant story, I wrote limit, yada, 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 and then I solved the limit, and at the end I determined it was not 0. A common error, logical error people make when solving problems like this is to actually put the equals 0 in that top line, because they basically have that formula in the box over there memorized, and the equals 0 kind of comes with the package. And so they put equals 0, but the equals 0 is a lie. It's not equal to 0. That's the whole thing. We're trying to check, is it equal to 0, and we determine it's not. So putting an equals 0 in that top line and letting it travel down with the rest of the problem is logically an error. So try not to do that. If you do that, I'll know what you mean, but it's poor style and it's not very logical thinking. So don't put the equals 0, because that's the whole thing you're investigating. Okay, I'll stop there. Please bring my registers back to me.